Alexander.
Thank you. Very glad to be here. The first half of the talk will actually be a general introduction to finite automata presentable structures, and the groups will come only in the last 10 or so minutes. The idea is, well, in classical mathematics, the structure is just something abstract, and you can define whatever you want in it without being concerned about algorithmic considerations. But maybe mid-20th century and perhaps even earlier, people thought it would be nice to actually have structures that are given by algorithms and not just something in some abstract mathematical world. By structure, I mean, of course, a set of elements and relations and functions defined on it, in our case, a countable set. And then algorithmic should mean that the elements are in some way given effectively, for instance, by strings, something you can write down, and those relations or functions should be given by algorithms, computable in the sense that Norm introduced. Now, that's a fairly large class. For instance, the natural numbers with plus and times is certainly computable in that sense, by what you learned in second grade or so. And however, this doesn't mean the structure is nice. What's nice? Well, nice would be, for instance, that I can decide any first-order fact about the structure. So the first-order theory, will it be decidable? Well, certainly not for the natural numbers. That's because my algorithms are just unrestricted, and that can lead to complicated structures, though they are computable. In this setting, I want to restrict the algorithms severely by saying that everything can be done by finite automata. And then some things go away that you think should be there, but like n, the natural numbers with multiplication is not presentable in that way. But on the upside, you get that the theory is decidable. For instance, n with addition is FA presentable, and we know its elementary theory is decidable. And that's perhaps how the story started. First, here's a picture of an arbitrary finite automaton. You've perhaps been in yesterday's talk, and you even know what weighted automata are now. It's got states and transitions, and it generally possesses a word by following the transitions. And if it gets to an accepting state when the word is finished, this won't work. Like the double circled one, then it says yes, and otherwise it says no. And in that way, the automaton will recognize a language, which means a set of strings over the alphabet, in this case 0, 1, that the automaton lives in. So this one, for instance, accepts the first string, but rejects the second string, as you can figure out by following that diagram. This angle is terrible, but welcome to move over to like. Yeah, so that's all I will tell you, but I'll give you one more example. Now let me go into my background on FA presentable structures. There was a Canadian person, Hodgson, in his PhD thesis. He wanted to give a new proof that Pressburg arithmetic is decidable. And what he did was actually define FA presentable structures and in some way show every of those structures has a decidable theory. So that's quite different from the classic proof, which does some sort of quantify elimination. So the actual founding paper was almost 20 years later by Kusainov and Nerode, when Kusainov was a postdoc at Cornell using, well, in Nerode's institute, the MSI. Well, that's long ago. For me, the story started in 2004 when I just had come to Auckland and I was attacked by people who wanted to study automatic structures. And Sasha here was one of them, who was a student back then. And I said, oh, wow, this is cool. Never heard of it, but well, let's work on it. And fresh energy, a new country, and actually a good paper came out of it shortly after, which has Buck, Kusainov, and Frank Stefan as co-authors. So what's the definition in a bit more detail? We have an FA recognizable language D of strings over a fixed alphabet, and the finite automaton should be able to check whether atomic relations hold. For each atomic relation, one finite automaton. So that includes the usual relations and also equalities. So equality is an atomic relation, and therefore it has to be recognizable by finite automata, and that's relevant because we allow it to be a non-trivial equivalence relation. We allow two strings to represent the same element. On occasion, that can be at least saving notation. So how will a automaton in more detail recognize the binary relation? It can't take one word and another word and sort of remember what the first was and then check the second. It has no arbitrary size memory, only constant size memory. Instead, it writes the words below each other, and we think of putting the k many elements for the carry relation on k tracks. And the FA actually processes stack symbols that are, well, symbols in the given alphabet written below each other. There's one technicality, this diamond, which I'll explain shortly. There's still only one head. So the automaton can only use one stack symbol at a time and goes through from left to right, and in the end comes to its decision. Now, some inputs could be shorter than others, and in that case, we fill it up with these technical diamond symbols because for what the automaton sees, all the things should have the same length. Okay, here's an example now. Yn plus is FA presentable. The alphabet is 0, 1, and that diamond. Domain is all these strings ending in 1. So there's binary numbers, but they're written in a reverse order because an automaton starts on the left. So that's certainly FA recognizable. Also the empty string, which is 0. And here's now my verification, actually not computation, verification that 5 plus 22 is 27. It doesn't have an output, that thing. So it actually has to verify rather than compute. And here you see how it does it. It uses the usual carry bit procedure and keeps the current carry in the constant size memory. That's the black. Oh. There we go. So the automaton has two states, no carry, beautiful color. Initially, we haven't seen a carry, so we start in a no carry state. And now there are transitions, such as what you do there in the picture. For instance, if I see 101, yeah, it's correct here, and there's still no carry, so I stay there. And second step was 011. Then I see 110, and then now incurs a carry. I go to the carry state, and so on. You can fill out the remaining ones. By default, if there's no transition, it rejects. So with a few more arrows, you can finish this automaton. That by being convinced that n plus is indeed FA presentable. All right. So now, as I said, the theory is decidable. In fact, the model checking problem is decidable, which means if I give a first order formula and corresponding number of elements in the structure, there's a uniform procedure to decide whether this first order formula holds for these elements. To prove this, you use induction on the length of phi, and that's tends to blow up the automata at the existential step and also at the negation, because well, think of it. You have a relation about two things, but one you're given, but actually you want to check whether something you can write on the second track will satisfy the relation. You can think of just guessing each time, non-deterministically. And existential quantifier should mean there's some guess which makes this hold. This naturally leads to an NFA, non-deterministic finite automata. And in fact, those are no stronger. They're equivalent as far as the recognized languages are concerned. And therefore, I can do this existential step, continue my induction. However, the size blows up exponentially, and therefore the theory is actually, well, it's primitive recursive. There's an arbitrary tower of 2's that you get. So that's the complexity class. But still, the theory is decidable, and also if I can first order interpret a structure in one that's already FA presentable, I get one that is itself FA presentable. So that's a nice closure property. Okay so far? So now what we started there, back there in Auckland was the complexity of the isomorphism relation on classes of A presentable structures. So that's pretty much the same hierarchy, but the lightphase versions of what Noam had. We encode an FA presentation by finitely many numbers that themselves express those finitely many automata. And now I can ask, given two descriptions, are these structures described actually isomorphic? How complex is that? Use my usual hierarchies. Buscellori and Liu showed for rather simple-minded type of structures, namely equivalence relations. This is pi1 complete. Beautiful little known paper using Hilbert's tens problem somewhere down the line. So it's pi1 complete to see whether two automata describe isomorphic equivalence relations. For graphs, as we showed back then, it's sigma 1 complete. So very complicated. This also means if there's an isomorphism, it's not necessarily computable. Can't be always computable. It could be that two things are isomorphic, but in some crazy way. So I can also try to classify all structures in a class. For particular classes such as Boolean algebras, this has been done in the same paper. So try to classify which structures in a particular class are FA presentable. And if you can do it, it would likely show that the isomorphism problem is decidable. Because there are many. So here's a bit more detail now. The complex side, as I said, we showed isomorphism problem is sigma 1 complete by actually looking at the configuration graph of Turing machines. So the nodes are the configurations and the transitions can go from one to the next. And you can massage your machine a bit and make those trees actually. Make it reversible. They are successor trees, meaning trees given by the successor relation. And in the same paper I mentioned already, 9 years later, people showed for linear orders, the isomorphism problem is also sigma 1 complete. Especially graphs, if you want. It is high. They almost started from computable linear orders and then turned them into FA presentable linear orders. So that's a nice result. And now what about the simple side? Yes, for Boolean algebras, there are very few possibilities. Let's have one that's certainly FA presentable, the finite or cofinite subsets of the natural numbers. We represent the finite set by ones in the right places, and then you give one more indicator whether you mean the set or its complement. You can certainly FA recognize all the operations, the Boolean operations, so that makes that Boolean algebra W FA presentable. Now our result from back then says that basically these are all, for infinite Boolean algebras, these and their powers are all possibilities. So any Boolean algebra that's infinite is of the form Wn for some n. And that now makes the, it first shows that a very general one, the free countable Boolean algebra is not FA presentable. It's not of this kind. Bad luck. And also shows the isomorphism problem is decidable. Not right away, but what this corollary actually does is take the presentation and you check it's a Boolean algebra because the theory is decidable. You can check that. And then you can, knowing that it's one of the W to the n's, actually figure out which n you have from the presentation. So that's all algorithmic because automata also nice, and therefore the isomorphism problem is decidable. Wouldn't it be nice to have a richer class where it's still decidable? Well, hard to get by. This is a very restricted class. So for several classes, it hasn't been determined actually what the complexity of isomorphism is. Very general classes taught in first algebra courses such as groups, abelian groups, and rings. We know not whether it's decidable. You can go from two directions. You can prove limiting results on the structures, like for Boolean algebras, and you can, from the lower bound, sort of get interesting examples of structures in the class, thereby trying to show it may be complicated. This has been done for these all these classes, and often the limiting side is more successful, but in some cases we do have interesting examples, and this I will do in the remaining time for groups. Remaining time meaning 10 minutes?
Should be no, finish at 30, well, I mean, let's say 35, so yeah, you have 10 minutes or more.
Yeah, all right. More. Yeah, okay, yeah. Do my best. So now here's the actual title of the talk. FA presentable groups, examples, constructions. Groups are certainly fundamental mathematical objects. There's symmetry. Groups will appear. I work a lot on them in all sorts of contexts recently, but they appear in fields as far away as quantum physics, crystallography, and maybe other things I don't know about. They have a very, very rich effective theory as well. And in fact, some of this computable stuff has been implemented. In fact, there's these systems like GAP and Magma. You know who owns Magma? Canon, yeah, somewhere here. It's proprietary. GAP is GAP is open source, and both are very useful. And it's actually exciting that some of these groups and structures aren't just abstractly computable, but you can practically compute with them, even in groups. Systems have packages for polycyclic groups and whatnot, and recently even uncountable groups. People have tried to practically compute with them. So it's not something that looks more concrete, but isn't actually. It's actually more concrete because it can be practically applied. Back to this. So here are some examples of FA presentable groups, the integers with addition, and also additive group of rationals where the denominator is the power of some k. For all these, you can easily write FA presentations. There are Prüfer groups, many quotients of Rk by Z, and infinite powers of S, where S is any finite group. So those are all obviously FA presentable. I mean, here the direct power. So you are zero eventually. Else it doesn't work. And then you can just make one symbol per group, per element of S, and go through. So there are three constructions I want to mention to get new FA presentable groups from existing ones. Some are quite dated already, but useful. With the book I wrote a paper in 2009 where we showed if I have an extension of an FA presentable group by finite index, and that group is also abelian, then it's FA presentable. So I can go up finitely many layers, so to speak, and retain FA presentable. Another example was take an abelian group and inside take the sum of two FA presentable subgroups. And also the intersection has to be A recognized like this. So this is L, which is big, but you have two groups that somehow are a presentable two intersection also have to be FA recognizable. And in that case, the sum, the amalgam, as people call it, is FA presentable. And that we use to make a rigid abelian group of rank 2. If you think of a abelian group, there's always trivial endomorphisms x times nx, x to nx. But rigid means these are the only ones. And that suddenly means you can't write a group as a product of simpler groups. It's indecomposable. So this is the goal of finding complicated examples. And here's one. More recently, we have with Frank Stefan, just a paper appeared that built an FA presentable group as a central extension of an abelian group by another. Something divided cycle has to be FA recognizable. So that's another example to build complicated groups out of simpler ones, and they're FA presentable. I'll tell you what these look like. Sorry, this gets a bit mathematical, but maybe you can get the gist of it. So these groups are nilpotent 2 and have exponent p. Nilpotent 2 means this thing about commutators here. And exponent p just means x to the p is e for any x. Yeah. So these are very easy groups. They're the next thing after abelian. CP is the variety class of such groups. With both properties. P is usually not 2. And now we defined two classes of groups, GP and HP. And both are infinitely generated. So you have generators here, x0, x1, x2, all of exponent P. And now you have to say what the commutators are. Remember, this is the commutator. The real term of the group elements. And in this presentation, you just say what it is. And for GP, there's only one commutator. It's always the same. Then the I is less than J is the Z, and if I is greater than J is Z minus 1, of course, then. So these are called extra special P groups, and they've been studied widely. We gave an FA presentation of that group. It's an interesting group, rather theoretically, also it's super finite and omega categorical and lots of other stuff. If anybody here cares about those notions. For HP, we say it should always be the same depending on the larger index. So I made infinitely many generators. That K is x0, xk. Always the same. But these ZKs are independent. So you have a much bigger center now, but still the group is FA presentable. So that's the most complicated example we can produce, allowing infinitely many commutators that only depend on the larger index. All right. So that's in this information processing letters paper. And now, lastly, the non-examples. I told you about n times already. That's a non-example. But among groups, there are also many known. If I make this slightly more complicated and now say that all these elements should be independent, they should never be equal unless you accept that x commutator of xk and xi is the inverse of the commutator of xi and xk. So all these things in the center are independent. Then I make a free group of infinite rank in that variety. Big center. We have a copy of Z by PZ to the omega down here in the center, all generated by the I case really generated. So that group is no longer FA presentable. It's in the paper. The idea is that well, in an FA presentation, the operations cannot increase length arbitrarily. They will has to be bound on the length that you can produce. And that means that these strings representing all the YIKs must be pretty short, and therefore the linear combinations also. But because it's freely generated by these commutators, there are now more elements than there are strings, than there's space in the strings of that length. So that gives a contradiction. Actual proof is 2 pages or so. Yeah, but that's the idea that we started with, and took a bit of sweat to work it out. But that's a non-example. And here's, I think I'll skip this for time reason, but we have a result with Thomas that severely restricts the finitely generated subgroups. They all have to be abelian by finite. So the subgroups are quite restricted. They're finitely generated. And it's too mathematical. So that's the big result from shortly after we worked on this chunk of someone from descriptive set theory used Feynman's lemma to show Qn plus is not FA presentable. That was a big question back then. And he used this additive combinatorics to show it cannot be. Brown and Stringman did after generalized this and showed that groups that are an extension of a finite direct sum of prefer groups by a finitely generated free abelian group, they can never be FA presentable. So that means there's a sequence like this. In particular, if G has rank 1, and is FA presentable, it has to be this RK group I mentioned earlier, C of 1 over K. So that's a strong restriction, but we still really don't know what these abelian groups are on the positive side. We don't know, for instance, if I restrict it to 1 prime in the denominator, not several, whether I can have an indecomposable subgroup of rank at least 2. That's unknown. With Lupini, who wasn't ranking back then, but we worked a bit on this and looked at a group of extensions and showed it has an effective isomorphism with the p-adic integers. And that could be useful because these groups that we are after are described as an extension of Z by Z of 1 over P. But it's also interesting because it effectivizes an age-old theorem by Allenbeck and MacLane from the 1940s, where we show here this is actually an effective theorem in a special setting. The logic block is something that's been running for a while and where I and other people put arbitrary maths, hopefully true, but things that can't necessarily be published but can be useful. So it's there, but Lupini lost interest in this and it's not published otherwise. So that's the non-examples. Remember, I've told you mainly about Sankovs, that Q plus is not FA presentable, and I told you about a more recent example of the free group in this variety, which is not FA presentable by a growth argument. But it's not quite clear what this class of FA presentable groups actually is, or even in the abelian case, let alone what the complexity of isomorphism is. So that's an open problem. This area has sort of boom and bust cycles. People get in and leave it, so it's not like people worked on it continuously, including me. But there's a stream of papers with a couple of these breaks, and maybe eventually by new people those problems would be resolved.